Hey folks, in this video we're going to look at FRQ number 3 and FRQ number 4, which are the two FRQ structures that are used in Unit 3's cumulative exam. First, starting with FRQ 3, which is titled Modeling a Periodic Context. This FRQ will always be no calculator. It will always cover only Unit 3, just the trigonometry sections, not the polar sections. And it will always be constructing a sinusoidal function from some sort of real-world scenario. So there's going to be an application that goes along with it. We also know that in this FRQ there's going to be three parts, A, B, and C. Part A is going to be labeling a graph that doesn't have any scale or any axes, and there will always be multiple correct answers for this portion. Part B will always be using that graph to create a sine or cosine function model, which is an equation. They will choose whether it is sine or cosine, and again, there's going to be multiple correct answers for Part B as well. In Part C, they will choose a specific interval of the graph, and our task is to analyze the behavior of that interval, and then also to analyze the rate of change of the model on that interval. Here's an example of what FRQ3 could look like. There's almost always a figure that's not necessarily drawn to scale, and then a paragraph to start off explaining the real-world context. So here we have a scenario with a person working out. It says, to strengthen his muscles, Drew performs dumbbell curls where he raises and lowers a dumbbell by lowering his elbow. When his arm is extended at his side, the middle of the dumbbell is 33 inches from the ground. The length from Drew's elbow to his palm where he is gripping the middle of the dumbbell is 11 inches. Drew begins with his right hand extended at his side, then completes one full curl in 4 seconds. A full curl consists of raising and lowering the dumbbell. He continues performing the curls in a pattern for a minute. The sinusoidal function h models the distance between the middle of the dumbbell in Drew's right hand and the ground in inches as a function of time t in seconds. All right, before I jump into the graph, I'm going to pick out some key information and label the diagram to help me with some of these measurements. Specifically, I'm looking for time and also height or the distance between the dumbbell and the ground. So first it says that when his arm is extended down at his side, the middle of the dumbbell is 33 inches from the ground. So that would be this distance here is 33. Another important measurement that we have is the length from his elbow to his palm is 11 inches. So that means when he's lifting it up halfway or his arm is straight out, that would be 11 inches higher. And then when he's all the way up, that would be 11 inches above that. It also says that at time 0, he's beginning with his hand extended at his side, and it takes 4 seconds for one curl. So at the bottom would be time 0 and also time 4. All right, so now on to the graph. I like to start with the output values, the y values. And it looks like here his minimum height is going to be 33, so that needs to be the bottom of those vertical values. 11 inches above that would be 44. That's going to be the midline when his arm is halfway up to the top of the curl. And at the top, it'd be 11 inches above that, so it's going to be 55 inches off the ground. For time 0 has to be when the weight is at the lowest. So it is possible for time j to be time 0, in which case points F and G would have a negative time. If we prefer not to deal with a negative time value, then we would want to extend our graph off to the left before point F to find when we would have time 0, and then point J would be the end of that first curl, which would be 4 seconds later. So assuming we don't want a negative time, I'll use these values as kind of the starting spot. Point F would be halfway through that first curl, so that's going to be 2 seconds in. And it looks like G then is going to be 3 seconds, halfway between 2 and 4. So each of these increments between consecutive points is 1 second. So point K would be at 5 seconds, P would be at 6. If you continued that time, the next end of the curl when we're back down at the bottom would be 8 seconds, which is 4 seconds after J. So the coordinates for point F would be 2, 55. G would be 3, 44. J is 4, 33. K is 5, 44. And P is 6, 55. You do not need to declare units. Part B now is going to ask us to write an equation for that graph. And again, it will declare whether we are supposed to use a sine or cosine function. So in this example, it says the function h can be written in the form h of t equals a times cosine of b times t plus c plus d. So the fact that it's cosine and not sine is going to influence my phase shift or c value. But before we get there, I'm going to start with the vertical values, a and d. D is going to be the midline value, the vertical shift, which in this case is 44. A is the amplitude, the distance between the midline and the extrema, which is 11. Next up, for the horizontal values, we're going to look at B, which is related to the period but not equal to the period. The B value is going to be 2 pi divided by the period. The period is the length of one cycle, which in this case is 4 seconds. 2 pi over 4 simplifies to pi over 2. Now for the phase shift, since we have a cosine function, we're thinking about how the cosine wave starts at a maximum, decreases, and goes back up. That maximum should be at 0 at a y-intercept, and now I can see that maximum is at 2 seconds, which means we've had a shift to the right 2 units, which means our c value is going to be a -2. You are allowed to leave your values in a list like this, or you can write it out as an equation. And if you prefer the equation, here's what that would look like. Y equals 11 times the cosine of 2, parentheses, t minus 2, close both parentheses, plus 44. In the last part, part C, they're going to draw your attention to one specific section of this wave, and it's going to name 2 points to look at. So here it says the t-coordinate of J is T1, and the t-coordinate of K is T2. So we're looking at this section between J and K. It says on that interval, is the function positive or negative? Is it increasing or decreasing? So the function being positive or negative refers to the y values. All of the y values in that section are between 33 and 44, which is positive. So h is positive. Is it increasing or decreasing? Again, referring to the function. The function is increasing because those y values are increasing from 33 to 44. So we would say h is positive and increasing. Lastly, it says describe how the rate of change is changing. So not just is the rate of change positive or negative, but is it increasing or decreasing? So we see our shape here from J to K is concave up. That tells me that the rate of change is increasing. You could also say the rate of change is getting more positive. Now notice here it doesn't say explain how you know or justify your answer. So in this case, I would just leave my answer like this. I would stop it. If it did say explain how you know or justify your answer, I would add in a statement saying that I know this because the graph of the function on that interval is concave up. Now on to FRQ4. FRQ4 is what most people think of when they think of a traditional math test. It is symbolic manipulation. So lots of algebraic tools and solving strategies come into play here. On this FRQ, there's always no calculator. It covers topics from Unit 2 and Unit 3. So although in our cumulative we won't see any Unit 2 topics, it is possible for those Unit 2 function types of logarithmic and exponential to show up on FRQ4 on the AP exam. Instead, on the Unit 3 cumulative, we will just have trigonometric functions and their properties. There's no real-world context. There's no applications. There's 3 parts, A, B, and C. What we know about part A is that they will always involve 2 different functions. Usually they're different types, so it could be like 1 logarithmic and 1 trig, or 1 exponential and 1 trig. And in this first section, it's all about solving, simplifying, or rewriting. Same thing in part 2, you're going to see 2 new functions, and usually it's 2 different function types. Again, solving, simplifying, or rewriting. The last part, part 3 or part C, only has 1 function, and again, it could be any sort of task with algebraic manipulation, solving, simplifying, or rewriting. So altogether in FRQ4, we're expecting to see 5 different functions from either Unit 2 or Unit 3. Before the FRQ section, there's a set of directions that apply to all of the FRQs. These directions have been screenshotted here on this slide for us to look at ahead of time. And essentially they are general guidelines for every single question within the FRQ problems. So this first bullet point says, unless otherwise specified, the domain of function f is assumed to be the set of all real numbers for which f of x is a real number. And then it also says angle measures for all trigonometric functions are assumed to be in radians. And with that, we're also required to give our answers, if they are angles, in radians. Second bullet point, solutions to equations must be real numbers, so we don't have to give the imaginary solutions. Within that, though, we need to have exact values when reasonable. So exact values when we can without a calculator. And it gives some examples. So example, log base 2 of 8, that's a Unit 2 expression, but we could simplify that to 3, or cosine of pi over 2, or inverse sine of 1. Those are trig functions that we can evaluate using our unit circle knowledge without a calculator. So that means if you leave your answer as cosine of pi over 2, they will not give you full credit. Next up, we should always simplify by combining like terms and using what we know about exponential and logarithmic properties. So for example, 2x plus 3x should never be left. It should always be combined as 5x. Or if you have exponents like x to the 5th power divided by x squared, those should be written in simplified equivalent forms. And then lastly, probably the most important, is that for each part of the section, all work must be shown. Anything that leads you to your answer needs to be shown. That is considered your justification. They will not state this throughout. They will not say show your work within each FRQ. It is the expectation that we are doing that anytime we have a calculation or algebraic manipulation. Here are a few examples of what FRQ4 tasks could look like, and we'll specifically look at some tasks that involve Unit 3's function types with trigonometry. So in part A here, we have a single function, but note that in the real AP exam and in our cumulative, there will be a second trig function. So this one just has one function, function g, and you can see it's quite a complex trig function. And our goal is to rewrite this function g using only one trig function. They do not clarify what that trig function is. So we're going to use our knowledge of identities and make some substitutions and see what we can simplify and combine. So right away within the numerator, one expression that stands out to me is this tangent of x. I know that tangent can be rewritten as sine over cosine. So that might be a substitution I might want to play. It could also be written as 1 over cotangent. I don't like that second option as much, since when I look at the rest of this function g, I don't see cotangent anywhere, so it doesn't seem like that would simplify with anything. I also see 1 minus sine squared x, which kind of reminds me of the Pythagorean identities, specifically that first one, sine squared x plus cosine squared x equals 1. If I subtract sine squared from both sides, I get cosine squared x is equal to 1 minus sine squared x. So that would be another substitution option. I like that one because I see a cosine in the bottom. I feel like I have enough to get started, so I'm going to make those substitutions and see what we get. So in our numerator, rather than tangent, we're going to have sine over cosine. And rather than 1 minus sine squared, I'm going to change that to cosine squared. I'm going to keep that denominator cosine of x for now. From here, there's a couple different ways we could start to simplify. The cosine squared from the numerator and the cosine from denominator are standing out to me. So one of those cosines is going to get eliminated. So my denominator is going to disappear here. And then in our numerator, we would just have a single cosine of x. So I'm getting sine of x over cosine of x. That tangent of x is where that came from. And then a single cosine of x in the numerator. Again, we're going to have more simplifying out. The cosine from tangent and the cosine from 1 minus sine squared are going to eliminate each other, and we're going to be left with just sine of x. So all of my work is shown. It's clear and easy to follow what the substitutions are. You want to be careful with crossing things out. It still needs to be legible so that the person evaluating your work can follow your logic clearly. I've displayed my work more horizontally because of the Google slide structure that I'm using. You can also show your work vertically, and I know that I am done because I've reached my goal of having only one trig function, just sine of x. Here's another example of a task we could see within FRQ4. Here's part B of this example. Just again, note that part B would have a second function. It could be trigonometric, exponential, or logarithmic. My new function here is function k, which I see as an inverse cosine. Function k is defined by the inverse cosine of 5x, And here our task is to solve. It says solve where this function k is equal to 2 pi over 3 over the domain of k. So setting this one up algebraically, we're going to set function k equal to 2 pi over 3. Using what I know about inverses, I know that if I have a trig expression like y equals cosine of x, that would be equivalent to saying x is equal to the inverse cosine of y. So I'm going to use that to kind of go backwards into a cosine equation. So inverse cosine of 5x equals 2 pi over 3. That means 5x is equal to the cosine of 2 pi over 3. This is where we're going to use our knowledge of the unit circle to simplify that right-hand side. Cosine of 2 pi over 3 is a negative 1/2. It can be helpful to sketch out that unit circle with that angle 2 pi over 3 just to double check those values, especially whether that's negative or positive. We're almost done here. To solve for x, we're going to multiply both sides by 1/5, or you could think of it as dividing by 5. Here we get a final solution of negative 1/10. Last up is part C. Part C will have the fifth and final function. It should be different than all of the others that we've seen throughout this FRQ4. Here we have function m, which is defined by 6 times the cosecant of x minus pi over 6. And our task is to find all the values in the domain of m that yield an output value of 12. So part of the challenge in this one is interpreting that sentence. We want the output to be 12, so we're solving for when this function equals 12. And it says find all the values in the domain, so we're solving for x. Now cosecant doesn't have any domain restrictions, so that means we're going to have infinitely many solutions. And I'm going to have to make sure at the end that I structure my solutions to include that infinite amount. So for setting up this equation, we get 6 times the cosecant of x minus pi over 6 equals 12. We want to isolate that cosecant expression, so we're going to divide both sides by 6. We get cosecant of x minus pi over 6 is equal to 2. Now, as much as I love these reciprocal functions, I would much rather work with sine than cosecant. So we're going to rewrite our equation using sine. Since sine is the reciprocal of cosecant, the sine of x minus pi over 6 would be the reciprocal of 2, which is 1/2. At this point, I'm going to think about the unit circle and look for where the sine ratio is positive 1/2. That's going to happen twice at pi over 6 and at 5 pi over 6. Now when we set up our equations, we have to be careful because the inside of that trig expression is not just x, it is x minus pi over 6. So we have x minus pi over 6 is equal to pi over 6, and x minus pi over 6 is equal to 5 pi over 6. To solve both of those for x, we're going to do the same thing and add pi over 6, giving us x is equal to 2 pi over 6, which would be pi over 3. And x is equal to 6 pi over 6, which is just pi. Our infinite solutions adjust our solutions just a little bit more than that. After we find those angles, we need all of the coterminal angles, so we're going to add on plus 2 pi times k, where k is an integer. we need both equations and that expression where k is an integer in our final solution. That wraps up this video on FRQ 3 and 4. One final note is that these two FRQs are given at the same time. They go together because they are the two no calculator FRQs, and you are given 30 minutes total to complete them both. So you want to estimate spending about 15 minutes on each FRQ.